Hey everyone, and welcome to this explainer. Today we're taking a really fascinating bottom-up neural journey. We are going to focus our lens entirely on section 5.3, neural frequency selectivity. We'll be unpacking the sheer brilliance of how raw acoustic energy in your ear is translated into highly specific, readable neural signals for your brain.
Okay, let's just quickly breeze through our roadmap for this bottom-up journey. We'll kick things off with tuning in auditory nerves, then we'll get into nonlinearity and rate functions, check out the incredibly cool phenomenon of suppression in auditory nerves, and wrap up with central auditory system tuning. All right, first up, tuning in auditory nerves, the micro-level connection. This is the exact moment where a physical vibration transforms into electricity. We have to start right at the physical connection point. Think about the sheer magic of this for a second. A physical sound wave has traveled through the air, bounced off your eardrum, and vibrated the fluid in your inner ear. Now imagine a tiny physiologist microelectrode recording the activity of just one single auditory nerve fiber. What we're looking for here is the absolute lowest sound volume, or level, needed to trigger a measurable electrical spike in that specific neuron across different frequencies. That threshold is what we call a frequency threshold tuning curve. Basically, it's the exact biological handoff from the loud, messy outside world to your internal neural network. So when researchers map out these tuning curves, a pretty fascinating pattern pops up depending entirely on the mathematical lens they use. If you plot out the characteristic frequencies, the specific pitch where each neuron is the most sensitive, on a standard linear scale, the absolute bandwidths of these filters seem to increase as the pitch goes up. It honestly looks like the tuning just gets wider and messier. But human hearing doesn't really work on a linear scale, does it? Nope. When you shift to a logarithmic scale, which is way closer to how we actually perceive pitch, where equal distances mean equal frequency ratios, it's a whole different story. The relative bandwidths actually decrease as the characteristic frequency increases. It's all beautifully systematic once you look at it the right way. The overarching takeaway here is super simple, but it's profound. Because each auditory nerve fiber connects to just one single inner hair cell, this direct biological link means the neural tuning perfectly mimics the mechanical tuning of the basilar membrane. And why is this so exciting for scientists? Well, trying to directly measure the microscopic physical vibrations of the basilar membrane inside a living ear is incredibly hard. But by tapping into the nerve and just recording these firing rates, researchers get a perfect, clear window into how the cochlea selects frequencies. Moving right along to section 2, nonlinearity and rate functions. Let's see what happens when we throw different sound intensities into the mix. To really grasp how our ears handle volume, we have to look at two totally distinct types of fibers working together. First up, you've got high spontaneous rate fibers. Think of these like a super sensitive hair trigger alarm system. They pick up the absolute faintest movements of the basilar membrane. I mean, even a whisper sets them off. Their firing rate shoots up incredibly fast, but the catch is they saturate or max out very early with steep functions. Once the sound is even moderately loud, they literally can't fire any faster. On the flip side, we have low spontaneous rate fibers. These are more like a heavy bank vault door. They need much louder sounds to even wake up and start firing. Because they're physically harder to move, they have shallow functions and max out at way higher sound levels. Working together, these two give us the massive dynamic range we need to hear a pin drop and still survive a rock concert. And the underlying research proves this beautifully in action. If you test a nerve fiber that is perfectly tuned for a best frequency of 20 kilohertz, and you play a pure tone exactly at that pitch, the neuron's firing rate actually grows pretty slowly and shallowly as you turn up the volume. This is the cochlea's built-in mechanical compression at work. But drop the pitch of the tone just slightly below that best frequency, down to 17 kilohertz, and the response totally flips. The firing rate rockets straight up. Why does a tiny shift in pitch completely change the game? Because the basilar membrane's response to tones just below its sweet spot is basically linear. There's zero compression happening there. The nerve's firing rate is hopelessly bound to the exact physical mechanics of the inner ear. Next up, section 3, suppression in auditory nerves. This is where we see what happens when multiple sound frequencies try to compete at the exact same time. A direct consequence of that nonlinearity we just talked about is a really cool phenomenon known as two-tone suppression. Think about it. In the real world, we almost never hear purely isolated single tones, right? We're constantly bombarded by rich, overlapping waves of sound. Two-tone suppression happens when the neural response to one tone is actually turned down or suppressed by the arrival of a second tone.
It's not a glitch or your ear failing, it's an active mechanical dampening that keeps our auditory system from getting totally overloaded by complex noise.
To really visualize how this built-in volume control works, imagine an auditory nerve fiber perfectly tuned to 8,000 Hz. If you play a steady tone right at that 8,000 Hz mark, the nerve fires away predictably. But if you blast a second suppressor tone at very specific surrounding frequencies, it physically forces that nerve fiber's firing rate to plummet by at least 20%. The second tone is actively interfering with the mechanics of the first tone on the basilar membrane. It's an incredible biological feature, mapped out directly to ensure the most important signals actually cut through the background noise.
Finally, Section 4, Central Auditory System Tuning. The macro level. We're following these signals out of the ear and up into the brainstem. As these electrical signals travel up into the central auditory system, that incredibly organized frequency-to-place layout continues. In the cochlear nucleus alone, there are 3 separate regions, each with its own complete map of frequencies. But here's the crazy part. It doesn't just act like a passive relay station passing the same raw data along. The tuning properties start to heavily diversify. We begin seeing much broader tuning curves with multiple peaks that respond to complex harmonies. And amazingly, some neurons that are even sharper than the raw data originally measured back in the auditory nerve. The brain is actively messing with and refining the signal. So how exactly does your brain artificially sharpen these signals to make them even more precise than the actual ear? It uses a clever trick called lateral inhibition. It's kind of like a spotlight in a really dark room. To make the center beam look incredibly sharp and bright, the brain essentially darkens the area immediately surrounding it. An excitatory input comes in from one neuron, but it's accompanied by inhibitory dampening signals from the neighboring neurons that represent the frequencies just on either side. This lateral inhibition artificially turns down the volume of the surrounding frequencies, sculpting the tuning groove to be razor sharp. It shows us that the brain isn't just passively listening, it's actively shaping the raw data. So, what does this all mean for us? As we wrap up this explainer, I really want you to consider how this bottom-up neural architecture, from the threshold of a single tiny hair cell to the complex inhibitory spotlighting in your brainstem, is the very foundation of your reality. Without this highly specific, intensely refined neural frequency selectivity, our world would be nothing but a chaotic, blurred mess of noise. Instead, it's the exact mechanism that lets you hear the beautiful shifting timbre of a cello or decode the rapid-fire complexities of human speech. Think about that the next time you manage to effortlessly focus in on a friend's voice at a loud, crowded party. It's an absolute marvel of biological engineering, and it is happening inside your head every single second.